Passive cooling of building using glycerin and paraffin wax with perlite as phase-changing materials. Abstract: the exponential increase in population growth has led to increase in high consumption of natural resources, which directly and indirectly is the source of liberation of CO2 in the atmosphere. Along with the construction industry, which is also a major source of liberation of greenhouse gases, active cooling devices such as the air conditioners and refrigerators also become the major source of emission of greenhouse gases. In order to control the room temperature by passive method, phase-changing materials, PCM, can be used in buildings. PCMs or latent heat storage materials are generally materials with large specific latent heat capacity. PCMs used in buildings will typically melt and solidify within a range of 1830 OC and are normally integrated in the building fabric. They can be used in the built environment to reduce internal temperature change by storing latent heat in the solid liquid or liquid gas phase change of a material. PCMs are found to store 5 to 14 times more thermal energy per unit volume than conventional thermal storage materials. The main objective of this project is to obtain ambient temperature within buildings and to reduce the usage of the active cooling machineries which releases greenhouse gases responsible for Earth's temperature rise. Telkes and Tyaghiare are the first researchers, who have undertaken the work on application of PCMs in buildings in 1975 and concluded that they can be incorporated with ordinary building materials. Organic PCMs like paraffin wax and glycerin are used and infiltrated with cement mortar. To prevent the leakage of these PCMs, perlite is used. The objective of the present work is to study the effects of various types of PCM including glycerin, paraffin wax, and perlite with paraffin wax in control of the room temperature from mortar plastered brick masonry model and comparing the results by simulating in software. Keywords: phase change materials, passive cooling in building, paraffin wax, glycerin, perlite. Introduction. The major causes of global warming are by carbon dioxide, CO2, which is an important greenhouse gas released through human actions such as burning fossil fuels and deforestation, as well as natural processes such as respiration and upsurge of volcanoes. It is expected that an increase of +1 degree C of room temperature in years. PCM is a material with a high heat of fusion which, melting and solidifying at a certain temperature, is capable of storing and discharging large quantities of energy. When the outside temperature is more than ambient temperature, the PCM changes to liquid phase and prevents the entry of heat inside. When the outside temperature is less than ambient temperature, the PCM changes to solid phase and prevents the entry of heat inside. The phase change materials are basically classified into two types, namely organic PCM and inorganic PCM. The organic PCMs are naturally available materials such as lauric acid, paraffin carbons, formic acid, glycerin, which are safe, stable, freeze at lesser drop in temperature and are recyclable. However, they have low thermal conductivity in their solid state and are most costly. The inorganic PCMs such as sodium sulfate, sodium chloride, aluminium, gold, copper, silver, titanium, etc. are chemicals which have high volumetric latent heat storage capacity, sharp melting point, high thermal conductivity and are relatively low cost. However, their change of volume is very high and often become defective after in due course. The study of A.Yahya et al. 2011 showed that the application of PCM slab panels could effectively reduce the energy consumption through active cooling systems. Application of PCM wallboards in building delivers latent heat storage throughout the building envelope. Arash Bastani et al. 2015. The incorporation of a PCM layer into an external building wall reduced the magnitude of the sudden heat flux through the wall. Nisab Ahamed al. 2013. An evaluation of a brick with and without PCM showed a temperature difference of 3.78 degrees Celsius. Concrete prepared with 10%, 15%, and 20% of paraffin wax which has melting point 26, showed up to 20% much lower temperature than the blank sample. The temperature difference value is about 3.6 OC in heating condition and is about 2.4 OC in cooling condition. Qing Wang et al. 2012. Perlite, diatomite, expanded graphite, and silica fume are commonly used with PCM to prevent leakage and to attain the required strength. Hwikyong Lee et al. 2014. Highest compressive strength was obtained while mixing the paraffin wax and the hydrophobic fumed silica in cement mortar, where leakage of paraffin can be prevented by adding hydrophobic fumed silica. PCMs may increase the thermal mass of lightweight buildings and then equalize the indoor temperature swings by which peak load flowing could be achieved. Qiaobing Zhou, et al. 2011. The simulations, carried out in PCM wallboards, showed a potential reduction of 2°C in the peak indoor air temperature. G. Evola, et al. 2013. The heat flux at the indoor space can be reduced by 17.55% when 3 PCM cylinders are introduced placed at the center line of bricks. Esam M. Alawati, et al. 2008. PCM in conventional and alveolar brick construction reduced the energy consumption compared with the same cubicle without PCM. A. Kastel, et al. 2010. The use of PCM in brick walls is helpful for the thermal insulation, temperature hysteresis, and thermal comfort for occupants. Chinbin Zhang, et al. 2011. Compared to a brick wall, gypsum board with 45% PCM stores 5 times more energy per unit mass, 9.5 times more energy and about 3 times more energy per unit mass than an ordinary gypsum board. Alicia Oliver et al. 2012. The thermal amplitude is decreased in the interior domain with the increase of the PCM thickness. The model with the larger PCM thickness of 25 mm reduces about 22%. Tiago Silva, et al. 2012. PCM used is able to absorb the heat developing from the external thermal conditions, thereby changing its phase from solid to liquid. During the nighttime the PCM solidifies and releases the stored heat. The application of PCM led to a delay of about 6 hours in the heat flux peak, and a reduction of 25%. Paolo Principi, et al. 2012. A thermal analysis of a building concrete roof with vertical cylindrical holes filled with PCM showed that the heat flux at the indoor surface of the roof can be reduced between 12.04% and 17.26% depending on the operating month. Hashim.J. Al-Khalaf, et al. 2013. PCM in perforated brick rooms produced result with good effect of decreasing temperature peak, 1°C to 2.30°C, reducing temperature fluctuation and increasing the thermal inertia, and indicated the opportunity of PCM panel usage. Xiangfi Ikong, Shiley Ilu, et al. 2013. The use of silver nanoparticles in PCM paraffin wax enhances the ability of thermal energy storage of the materials. Pradeep.N. et al. 2020. From the review of literature, the most widely used PCM is paraffin wax. PCMs have a better temperature control while adding in cement mortar and plastering. Perlite prevents the leakage of PCM during exposing condition. Other PCMs, such as glycerin, can also be used in effective temperature control. 2 materials and methods. A. Material collection and model preparation. 4 numbers of brick masonry room models were prepared. Fig.1, A, B, C, with inner size 600 mm x 600 mm x 600 mm, covered by reinforced cement concrete, RCC, slab of size 600 mm x 600 mm x 75 mm M20 grade concrete with reinforcement 6 mm at 150 mm C/C both ways. The walls were made of red brick 150 mm thick with mortar and plastering by cement mortar, cm, 1:5 mix. A small opening of size 150 mm x 150 mm was provided on one wall to enable the study of temperature inside the room at regular intervals. The variation in the 4 models were the PCMs used in the cement mortar used between the bricks, inner and outer wall plaster. The PCMs used in the 3 models were 5% glycerin, 5% paraffin wax and 5% paraffin wax with perlite, the results of which were compared with the control mix of only cement mortar used. The 4 mixes are given in Table 1. The temperature variation in the 4 prototype models were studied for 30 days during morning, afternoon, and evening. The temperature readings were taken through using industrial temperature sensor for 12 hours per day. Also, to find the thermal variation in the prototype, ANSI modeling software was used to model the thermal variation of the 4 models with the same materials and dimensions and plotted to get the 2D thermal variation of brick, as shown in Fig.2. Fig.2 two-dimensional pattern of wall brick done using ANSI software. B. Physical properties test. The specific gravity of the raw materials including cement, fine aggregate and coarse aggregate were found as per standards, as 3.15, 2.65 and 2.65 respectively. The 4 mix proportions of cement mortar were tested for water absorption. The compressive strength of the mortar mixes were arrived as per IS 4031-1988, Part 6. To find the coefficient of thermal conductivity of a cement mortar with different proportions using Lee's disk apparatus. The thermal conductivity was calculated by using equation 1. K equals, asterisk, plus, asterisk, slash, slash, dash, asterisk, plus, slash slash K, 1. Where, m mass of the metal disc in kg. S specific heat capacity of the material of disc in J kg 1 K1. D thickness of a bad conductor in m. R radius of the metallic disc in m. H thickness of the metal disc in m. 1. Steady state temperature of the steam chamber OC, steady state temperature of the metal disc in OC, slash, rate of cooling at steady state temperature. 3. Results and discussion. The results of the compressive strength test, thermal conductivity test for the 4 mixes in the models have been tabulated below. A. Compressive strength test. The compressive strength of the mixes added with PCM showed lesser results than the control mortar mix CM. However, the strength of mortar in brick and plastering is immaterial when the brick walls are used in framed buildings and non-load bearing walls. B. Water absorption test. The water absorption test from Table 3 also showed results similar to the compressive strength test, where the absorption increased for the mortar mixes with PCMs but were within the limits. C. Thermal conductivity test, Lee's disk apparatus. Table 4 shows the results of the thermal conductivity value. In this, CMPP shows the lowest value of all others. High thermal conductivity are generally used in heat drop applications, and the materials of low thermal conductivity are used as thermal insulation. D. Temperature variation of outside, CM and CMG mixes. The variation of temperatures is shown in a graph for respective 12 hours timely readings. The Fig.3 shows the average temperature between outside temperature and CM without PCM and CMG. The CMG was found to give the better results with reduction in temperature of 3% during daytime and increase in temperature of 3% during nighttime. Fig.3 Temperature variation of outside, CM and CMG mixes. E. Temperature variation of outside, CM and CMP mixes. The Fig.4 shows the average temperature between outside temperature and CM without PCM and CMP. The CMP was found to give reduction in temperature of 2% during daytime and increase in temperature of 2% during nighttime. Fig.4 Temperature variation of outside, CM and CMP mixes. F. Temperature variation of outside, CM and CMPP mixes. Fig.5 shows the average temperature between outside temperature, CM without PCM and CMPP. The CMPP was found to give the better results with reduction in temperature of 5% during daytime and increase in temperature of 5% during nighttime. Fig.5 Temperature variation of outside, CM and CMPP mixes. G. Thermal variation from ANSI of CM with PCMs for 4 mixes at 9 am. To find the temperature reduction in each of the model wall bricks from outside surface to inner surface, a two-dimensional analysis of brick with CM and PCM were modeled and analyzed using ANSI software. These kinds of analysis were done and visualized the heat flux with all mixed proportions. Fig.6 shows the thermal conductivity results outside and inside the wall at 9 am for the 4 mixes. It is seen from the graph that CMPP shows the best thermal insulation. Fig. 0.6 Thermal variation from ANSI of CM with PCMs for 4 mixes at 9 am. H. Thermal variation from ANSI of CM with PCMs for 4 mixes at 12 noon. Fig. 0.7 shows the thermal variation analyzed by ANSI's software for 12 pm. In this, the fourth composition with paraffin and perlite shows the best thermal insulation for 12 pm. Fig. 0.7 Thermal variation from ANSI of CM with PCMs for 4 mixes at 12 noon. I. Thermal variation from ANSI of CM with PCMs for 4 mixes at 3 pm. Fig. 0.8 shows the thermal variation analyzed by ANSI's software for 3 pm. In this, the fourth composition with paraffin and perlite shows the best thermal insulation for 3 pm. Fig. 0.8 Thermal variation from ANSI of CM with PCMs for 4 mixes at 3 pm. J. Thermal variation from ANSI of CM with PCMs for 4 mixes at 6 pm. Fig. 0.9 shows the thermal variation analyzed by ANSI's software for 6 pm. In this, the fourth composition with paraffin and perlite shows the best in maintaining the ambient temperature during very cold period for 6 pm. Fig. 0.9 Thermal variation from ANSI of CM with PCMs for 4 mixes at 6 pm. K. Thermal variation from ANSI of CM with PCMs for 4 mixes at 9 pm. The above graph shows the thermal variation analyzed by ANSI's software for 9 pm. In this, the fourth composition with paraffin and perlite shows the best in maintaining the ambient temperature during very cold period for 9 pm. Fig. 0.10 Thermal variation from ANSI of CM with PCMs for 4 mixes at 9 pm.